Hi everybody, so today we're going to be talking about uniform circular motion and build upon some knowledge that you have from other subjects in order to really flesh out what's going on in this course. So let's start by drawing a circle. So I can say that this is my x component and this is my y component, and I can be very happy with that analysis. But if I wanted to use slightly different coordinates in order to model my circle, what I can say is that this is 0 degrees, this is 90 degrees, this is 180 degrees, this is 270 degrees, and then when I go the full circle, it's 360. So that's how I can talk about circles in terms of degrees. I can also talk about it in terms of radians. So radians are a dimensionless unit. So I know that's weird to say, but they are a dimensionless unit. So that means that we use them in terms of order to describe angles, but in actuality, what we actually have is radians. If we were to multiply it in terms of unit analysis, it doesn't always matter. So if we were to multiply radians by meters, we were still stuck with meters as our unit. So let's say that this axis is 0, this is pi over 2, this is just pi, this is 3 pi over 2, and then we end up at 2 pi. So we can say that our radius here is r and our angle here is theta. So r is a radius. We normally treat the radius in terms of meters. And then we can say that this right here is our arc length s. So s is arc length. And the equation in order to calculate it is equal to theta times r. But in order to do this, theta is in radians. This doesn't work if theta is in degrees, because then we have degree meters, and degrees is a unit. Meanwhile, if we were to multiply radians by meters, we are still left with meters. So S is basically the length of this little wedge of pi right here. So we can also think of theta as the angular displacement. And we'll get to that a little bit later. So now let's just say we have a circle. And at the end of the circle, we have a rock. And this rock is being swung around in a given direction. So as long as we're swinging a rock at basically a constant force, what happens is that we'll get an acceleration vector, because we'll have the different velocity vectors that are running tangent to the circle. But all these velocities are going to be the same. So velocity is constant. So that means that we do have an acceleration because we're looking at the magnitude of velocity. The direction's changing, so we'll get a centripetal acceleration. So V is constant, direction is changing. So we have acceleration. And so AC is the centripetal acceleration. And we can calculate it by using V squared divided by R. So this is one of the main equations of today's lecture. So this is our R. So we can also talk about angular velocity. So we know that our arc length is equal to r times theta. So if we were to take the derivative with respect to time on both sides, what we would get is ds divided by dt is equal to dr d theta plus d theta dt times r. So in this case, we're treating that dr is equal to a constant. So then we get ds divided by dt, and that's going to be equal to d theta dt times r. So I can treat this as the velocity itself, v, and here we're going to just be looking at the magnitude times omega times r. So this fancy w, omega, is the angular velocity. And we define it as equal to d theta divided by dt. And we can go in between the translational and the rotational velocity by multiplying the rotational velocity by our radius. So this is another two important equations that we're building in our use of physics. So if we have angular velocity, we can also have angular acceleration. So angular acceleration. So in angular acceleration, we're going to use this fancy fish. It's called alpha. And in angular acceleration, what we do is we take the derivative of the angular velocity with respect to time, and then we set that equal to the second derivative of the angular displacement with respect to time squared. So here what we have is that theta is angular displacement, the unit is radians, omega is angular velocity, the unit is radians per second, and then alpha is angular acceleration, and the unit is radians per second squared. And we can also use a similar relationship where if we were to take the derivative of the velocity, and we can say that the magnitude of our acceleration is going to be equal to alpha times r. So this is another couple useful equations in this work. So now let's think back to kinematics. So in kinematics, we learned that delta x is equal to v naught t plus 1/2 at squared. We know that v final is equal to v initial plus at. And then we have vf squared is equal to v naught squared plus 2a delta x. So here we have linear displacement, linear initial velocity, and linear acceleration. And we also have linear final velocity. And we can basically get similar equations if we have constant angular acceleration. So in kinematic, we need a constant acceleration. In this case, we need a constant angular acceleration. And then we have the analogs of delta theta is equal to omega naught t plus 1/2 alpha t squared. We have omega final is equal to omega initial plus alpha times t. Then we have omega final squared is equal to omega initial squared plus 2 alpha times delta theta. So we're basically using the same equations, only we're substituting our forms of angular velocity, angular acceleration, and angular displacement in the analogs for our linear cases. Now, looking back to our change in centripetal velocity, which causes the centripetal acceleration. So let's just say this is my circle, and I start at this point here, and I'm rotating this dot through an entire rotation. If I wanted to calculate the velocity, I would have to think about my arc length, and then I would have to think about my time, delta t. So here my arc length for the entire circle is equal to 2 pi r, and then my time for one full revolution is just going to be my period, since I know that the period, capital T, is going to be the time it takes for one revolution. So this is basically the basics of rotational motion. There's one more thing that we need to talk about, and we have directionality. So if we were looking at the translational situation, if we have someone that's moving east, or in this direction, we can say they're moving in the positive x direction, or if we're moving to the left or to the west, then it would be negative x. In terms of angles, we have clockwise and counterclockwise. So let's just say I have a disk, and we have to think about which way a clock goes. So if I were to look at a clock and I see that it is 9 o'clock, I know that the clock moves downwards, because that's 1, 2, 3, so on and so forth. So I can say with 100% certainty whether or not something is rotating clockwise, which we'll abbreviate CW, or if it's moving the other way, it's counterclockwise. So if we're in the counterclockwise, it's a little weird. It's going to be in the positive direction, and then clockwise is going to be in the negative direction. So that means if I'm changing my angular displacement and I'm moving in the clockwise fashion, it's going to be negative. If I have angular velocity and it's moving clockwise, it's going to be in the negative direction, and the same thing with angular acceleration. So anything that's moving clockwise is going to have a negative omega. And let's just say we have something speeding up in the clockwise direction, we're going to have a negative alpha. If we have that the object is slowing down or decelerating, then our alpha is going to be positive. So overall, directionality is extremely important, and this is just the overall convention. Why is it this way? I don't know, but this is the convention that we use. And with that, that is basically all of topic number 12. Let me know if you have any questions, comments, or concerns. You can